All right, guys, what we were doing last time was we were investigating under what conditions given a linear network will lead to maximum power transfer when we have a load. And we've gotten so far as saying we found a formula for the power, and there were two conditions that needed to be met for maximum power transfer. The first was the first partial derivative of the power with respect to the load reactance that had to be equal to zero. The second part was that the partial derivative of the power with respect to the load resistance had to be equal to zero. We haven't done that part. That's the part that we really want to concentrate on. So here we are continuing our investigation on maximum power transfer. So this is continued. And this is now part 2. And we're going to look at the partial of the power with respect to the load resistance, set it equal to 0, and see under what conditions that actually occurs, what constraints that imposes upon us. Right. Now, the power equation was quite a large one, and I'm going to reproduce it here. So it's the partial of the power with respect to the load resistance. So I'm going to take partial with respect to the load resistance of, and brace yourselves, it's a beast. It's the Thevenin voltage squared, or at least the magnitude of it, times the load resistance divided by, in the denominator, we have the sum of the Thevenin resistance plus the load resistance squared, plus the Thevenin reactance plus the load reactance quantity squared. This, and we wanted to take this partial derivative. Now, notice that that load resistance occurs there and there. So what we need to do is we actually need to use the quotient rule. So here, we're going to use the quotient rule to find this. On top of that, we will be setting equal to 0 and then solving to see what conditions or constraints we actually have. Now, way back in the day in high school, I learned the quotient rule using a little mnemonic. It was low d high minus high d low over low low. So it's the denominator times the first derivative of the numerator. So let's actually write that down. So the denominator here is R Thevenin plus R load squared plus X Thevenin plus X load squared. And now I'm going to take the partial derivative of the numerator with respect to R. That is that right there. And notice that very, 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 very beautifully, the R only appears there. The Thevenin voltage magnitude is constant. So this whole term, which I have here, is just 1, right? So I'm going to go ahead and simplify this. Hopefully you copied down what we have there, but the whole thing is just 1. So that's low d high minus high d low. So high is going to be RL times d low. Oh, and don't forget, I'm pulling out also the magnitude of the Thevenin voltage quantity squared in front. And here I'm going to take the partial with respect to R sub L of R Thevenin plus R load quantity squared plus X Thevenin R load quantity squared, and I'm taking the partial of this. Now I'm going to do the same thing. I'm going to do the simplification. Notice that when the partial derivative here pushes over to this term, that partial derivative is 0. Why? Because that doesn't depend on R load whatsoever. R load only appears there, and it appears within the parentheses. You can use the chain rule on that. You're going to bring down the 2, you're going to subtract 1 from the exponent, and then you're going to take the derivative of the inside, and that very, very easily and nicely turns into 2 R Thevenin plus R load. So here, this big, nasty partial derivative, and again, hopefully you can do this on your piece of paper as well. turns into something nice, beautiful, and simple. It's 2 times R Thevenin plus R load, like this, and divided by low, which is the denominator squared. So R Thevenin plus R load squared plus X Thevenin plus X load quantity squared, and this whole thing is going to be squared like this. And then we're actually going to set this equal to 0, right? Um, it's a horrendous calculus problem. It's something that you really need to take care and work through. But something's going to be kind of rather nice, right? Notice that the only way that this whole thing can be 0 is if the numerator of this is equal to 0, right? So one of the things that I'm going to do is I'm actually going to focus in on the numerator only. So here I'm going to set the numerator equal to 0, right? Now that means that we have the Thevenin voltage magnitude squared, and then we have R Thevenin plus R load quantity squared plus X Thevenin plus X load quantity squared. We would have actually multiplied this by 1, but that's exactly what we have. We don't need to do anything else. And then we're going to take into account this term. So here we have minus R load times 2 R Thevenin plus R load, like this, and that's equal to 0. Now notice that there is one solution here, right? So solution number 1 is the magnitude of the Thevenin voltage squared could be equal to 0. But again, if that's the case, then we get no power transfer. This is rejected. Right? We don't want this. The other thing is this huge nasty mess is equal to 0. And keep in mind that our goal is we want to solve for our load. Right? So here, the second solution is R Thevenin plus R load squared plus X Thevenin plus X load squared minus 2 R load R Thevenin plus R load is equal to 0. Now, this might look like a horrendous mess, and it kind of is. Keep in mind that we're also solving for a constraint on R load. But there's a few things that are going to be very nice. Notice that I can actually write out what this is very easily and what that is very easily, and there are going to be a number of very happy cancellations. So here what we actually have is R Thevenin squared plus 2 R Thevenin R load plus R load squared from that first term up here. So this and this are the same thing. The X Thevenin plus X load quantity squared, well, that just comes along for the ride. So I've taken into account that term and that term. The next thing that I want to do is I want to multiply out this whole thing, in which case I end up with minus 2 R load R Thevenin minus 2 R load quantity squared, and that's equal to 0, like this. So this whole mess up here is the same thing as this. And let's actually take a look, right? Notice that this first term right there, those completely cancel out, right? So this and this disappear. On top of that, and I'll put this in green, this term and that term, they combine to give us minus 2R load squared. Notice that's the only place where we have our load. So we can add it to the opposite side, right? So here, I'm going to rewrite the above equation. So I'm going to Oops, let's do this not in green, let's do this in black. So the above can be rewritten as R Thevenin squared plus X Thevenin plus XL quantity squared, and then minus our load squared is equal to 0. So that huge equation at the very top combines into this, or I can then solve for the R load in the following manner. I'm going to add this to the opposite side, take the square root. So it is the square root of R Thevenin squared plus X Thevenin plus X load quantity squared, square root. This is our second condition. So this is a second condition for max power transfer. Now let's actually go back and combine these things. So here, from part 1, we found that if you take the partial of the power with respect to the load reactance, set it equal to 0, what we found was that the X load had to equal minus X Thevenin. And now from part 2, we have now found that if you take the partial of the power with respect to the load resistance, set equal to 0, that can only happen is if R load is equal to the square root of R Thevenin squared plus X Thevenin plus X load squared like this. Right? This I'll call equation A. This I'll call equation B. And notice very, very easily and nicely, if I actually use A in B, right, then the conclusion is that R load is equal to R Thevenin quantity squared plus X Thevenin minus X Thevenin quantity squared. This term very happily drops out to 0, in which case we get that R load has to equal R Thevenin, right? So this is actually going to be condition C. So if I actually use condition A in condition B, because it's written in terms of the load reactance, and we come up with something simple, assembling all of the pieces, we will actually have max power transfer if Z load, which is R load plus JX load, but we just found R load has to equal R Thevenin, and X load had to equal minus X Thevenin over here. Very succinctly, we can actually say that this will be true is if I actually take the Thevenin impedance, take the complex conjugate, that should be the load resistance. So for max power to occur, we must have that the load impedance is not equal to the Thevenin impedance of the linear network. It must be equal to the complex conjugate of the Thevenin impedance. And that was actually what we were looking for. This is a massive result. I cannot explain to you how many places this result is actually used. We will take a look at one last situation. We actually do want to find how much maximum power can actually be extracted from the network, but we actually now just found the condition for max power transfer.